like the electron is over here at around 500,000 electron volts. And the neutrino is far less than an electron volt, something like 100 milli-electron volts. And so there's an enormous scale, almost a factor of a million, between the neutrino and the next lightest particle, which is the electron. And so just to give you a sense of what that is like, right, so an ant would be something like a milligram, and so a hedgehog is something like a kilogram. And so that gives you sort of the scale of distance between the mass of an ant versus a hedgehog. And a similar scale sort of exists between a hedgehog and, let's say, the biggest creatures we know of, the blue whale. And so just by looking at something like this, you will probably conclude, for example, that the ant must have a very different evolutionary history than the blue whale. And likewise, we suspect that the neutrino and its mass has a very different origin from the mass of other particles because it is so different. And as I mentioned before, or I alluded to in the beginning, the masses over here are actually governed by the Higgs boson, which was discovered at the LHC. And we believe that neutrinos possibly may have a completely different mechanism for getting its mass, one which actually makes it its own antiparticle. So that's somewhere now, I won't talk about that. And that's an interesting thing called the Etruscan shrew. So this is actually the smallest mammal in existence. It weighs barely a gram. Okay, so as far as why this is interesting, there's an interesting problem that when we go into the laboratory, we know energy can produce matter, but every time we do this, we create an equal amount of antimatter. And if we think about the Big Bang as a source of energy producing the matter in the universe, somehow an equal amount of antimatter should have been produced. And yet we don't see any of it. And so what happened to that antimatter is one of the big questions in physics we have today. And as it turns out, it's a very, very tiny effect. Our understanding is that at the beginning of the universe, matter and antimatter were probably created in equal proportions to about a part in 10 billion. All right, so if you had sort of a great, so 1 part in 10 billion, matter and antimatter were equal. They annihilated, and that one bit that's left over from that part in 10 billion accounts for all the matter we see in the universe. So you can see it's a very, very tiny imbalance. On the other hand, we can't seem to be able to explain even this tiny little bit of asymmetry. And so one of the leading theories right now is that somehow differences between neutrinos and antineutrinos may be responsible for this imbalance, and basically why the universe exists. Okay, and so one of the interesting things is that there is a parameter within the neutrino mixing, which we call delta. It's just a property that neutrinos have, which allows these neutrinos and antineutrinos to oscillate differently. And so this was a topic of an article in The Economist, of all places, around 5 years ago, where we first saw these neutrino transitions, which will actually allow an imbalance between the neutrino part and the antineutrino part. So as I mentioned, we have to send these neutrinos something like 1,000 kilometers to study this process in detail. And so in the US at Fermilab, we're mounting an extremely ambitious program where we are actually making a neutrino beam that will start at Fermilab, which is outside of Chicago, and get sent to a mine in South Dakota. And so you can see here, what's shown here is that protons from this accelerator complex are sort of pulled upwards and then sent downwards. And then basically the particles produced by protons interacting on a carbon target produce particles which in turn decay to produce the neutrinos, which will eventually go 1,300 kilometers to South Dakota. And so you can see that because you have to account for the Earth's curvature, the beam is pointed down slightly. There's actually a limit on how far we can dig for various geological reasons, and which is why we have to actually pull the proton beam up and then down in order to sort of get a little bit more headroom in order to make this happen. So another challenge here is that we're placing these detectors about a mile underground in South Dakota in a former gold mine. And within these detectors, there's also an enormous scale that we're talking about 4 17,000-ton detectors. So each of these detectors will be about something like 300 feet long and about 50 feet high and across. And not only that, they are also employing liquid argon, which is something like, basically we have to refrigerate this thing to minus 190 degrees Celsius. And so as a result, we also have to create enormous refrigerators which accommodate these large detectors. Now, what's amazing about these detectors is that across this entire volume, right, about the size of a football field, we can get sort of millimeter spatial resolution on the products of a neutrino interaction. And so it's this detail that we hope will allow us to give us a very, very precise sensitivity to the possibility that neutrinos and antineutrinos are behaving differently. Let me just, I think I'm out of time, so let me come to the conclusions. I've actually been in the neutrino business for only about 10 years now. And people always say it's the golden age of neutrinos, and it's still the golden age. And I think it's because, well, they're just really weird things, and every time you study them, you get an answer, and the answer is really, really strange. And usually we have a question, we get an answer, and the answer is so strange that we just have more questions. And as we see, neutrinos have some really peculiar patterns, among them which is the fact that they're extremely light. And we still don't really know how to explain this. And apart from the neutrino, we have the question of why the universe is matter-dominated, or in fact not exists at all, and why all the matter and antimatter that was produced in the universe didn't just annihilate and leave nothing. And so this new experiments which we're building today will allow us to see if this imbalance actually exists within neutrinos, and that possibly this imbalance is in fact the desperate solution to this very profound question about why the universe didn't just all annihilate away. So thank you very much.